All right, good morning. So uh I had someone reach out about the test date, and I realized that it felt kind of like an oversight because the test is scheduled for April 2nd, which is immediately after Easter, and that's not really my style. So I feel like, or I fear, that I might have forgotten about Easter there for a bit. And so um, what I want to do is to move the test until to the Thursday before Easter. So then you're free of me for Easter, and that might be nice. Kind of a well-deserved break. And so um if if there's problems with that, then please let me know as soon as you can because I do plan on changing it, but I don't like to change test dates typically. It's just this was my bad, an oversight. Um, and so test number 2 um, is scheduled for April 2nd. But I am moving it. Oops. But I am moving it to March 28th, moving it before Easter, so then you can have a proper break. And I know that you probably have other tests and things then, but um, so like I said, if that's a problem, then please let me know. Otherwise, I'll go ahead with that switch. It's also selfishly so that I can have similar test dates to the other sections of this course, and so or Steve's section in this case. And so he's got it before Easter, so I want to have it before Easter, and should have checked that out earlier. My apologies. So I'll move that. In terms of material, it's just whatever we reach uh, before then, that's what's on the test. So it's not going to be on the same amount of material as if we had the day before. Okay. So if you have questions about that, you can put them in the chat. I realized my computer was on mute earlier. So there's always that risk. Okay, so let's see here. So that's kind of important. Uh, Anything else I wanted to say there? Hmm, no. Okay. Wait, highlighter. That's not going to do very well. Some quick review. It was just on Tuesday, but we introduced hypothesis testing. Um, uh, yes. But yeah, just catch me at the end of class. So, uh, let's see, what did we do? We introduced kind of the concept of hypothesis testing, which is really kind of an intricate dance, right? There's so many ins and outs to keep track of, and we didn't even have a chance to do an example, and that's what I want to do today, and just kind of talk you through things. But hypothesis testing, we broke it up into 4 steps. Now I'm just going to outline the steps and just remind you of what they are, but I want to grab from the formula sheet first, which I think I moved in here. There. Yeah. Copy. Paste. Okay. So we're here in hypothesis testing, right? And just as a reminder, Step one is to state the hypotheses, which in our case, right, comes from here. For any one sample proportion question, right, type of question, the null hypothesis is going to be H naught is that P is equal to P naught, where P naught is the number that we want to compare our sample proportion to from the question, right? And so we haven't seen an example yet, but we will. And so the alternative, let's just say generically, is that P is not equal to P naught. Right, kind of the flip side of equal to. We could use less than or greater than, depending on the question, right? Step two is, I call it do the test, which in our case, or in the one sample proportion case, means calculate this Z. How far is P hat from P naught? Okay, and so here, Z is P hat minus P naught divided by the square root of P naught Q naught over N. Okay, that's the standard error of the hypothesized population, right? Instead of the standard error of P hat. So it just changed slightly from the confidence interval, right? Here in the confidence interval, we have P hat Q hat, right? And so just slightly different. Okay. Step three is find the p-value. Right, using the Z, right, we can find the p-value, which is the probability of seeing something as extreme or more extreme than what we saw, right, assuming that the null hypothesis is true. And so essentially that means find the probability of seeing something as extreme or more extreme than what we saw, assuming the null hypothesis is true. Assuming H naught is true. And I'll just show that that's a 0. Okay. Okay. Step 4 is your conclusion. Three parts to the conclusion. The first one, you have to compare the p-value to the alpha level, right? And so compare the p-value that you found to the alpha level. Remember, the alpha level is the significance level. It's an alpha. So the alpha level is the significance level, and the default is 0.05. And so, but we can set different confidence levels and, well, yeah, significance levels, but they're related to confidence levels. And so you compare the p-value to the alpha level, and then you're going to have a conclusion in terms of H naught, right? You did all your testing assuming H naught was true, and so then you either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. And we talked about the different sentence structures that you have, and those are your only two options, right? And so, so just kind of committing one to memory and then negating it would work. So conclusion in terms of H naught, followed by a conclusion in terms of the question. That's the one people love to forget. Okay. Okay. So in here, between step 1 and step 2, and maybe I should have Dang. Okay, I'm gonna get a little creative here. Gonna move this and this. I just need one line. There. In here, we said, well, we're not gonna do it last day, but we're gonna do it today. I want to introduce the conditions that we should be checking. Okay, and so in here, we should check the conditions. Okay. So this is the end of the review, but the conditions for a hypothesis test for one sample proportion are these. The first one, so I guess maybe verbally I'll remind you of the conditions for a confidence interval, right? The conditions for a confidence interval is independence, right? And how do we ensure that our observations are independent of each other? By randomly sampling, right? And then we had that optional n less than 10% of the population condition, which I tend to ignore. And then we said, okay, well, for the sample size condition or the normality condition, I need to have at least 10 observed successes and at least 10 observed failures. So now for hypothesis testing, we follow almost the same conditions with a switch to the normality condition, but the independence condition stays the same. And so the first part, the independence condition, is first randomly sampled, right? That ensures that we have independent observations, or we can assume we have independent observations. The second thing, which is optional, if you forget about it, that's totally fine. The n less than 10% of the population condition. Now notice, right, I'll just make a note that this is the same as for the confidence interval, right? So once you've got those kind of jotted down somewhere, then you're good to go. It's the normality condition. Normality, or the sample size calculate or condition. Okay. This one is different from the confidence interval. Just slightly, almost confusingly, very similar. Okay. So now we want to make sure that we have at least 10 expected successes. Okay. At least 10 expected successes. Okay. We could also say hypothesized, if it helps. How we're going to find how many expected successes we have, we're going to take n times p naught. Now that p naught is the hypothesized proportion. So n times p naught, as opposed to n times p hat, which is the number of successes observed, right? And so here, n times p naught has to be greater than or equal to 10, where p naught is from the null hypothesis that p is equal to p naught. And so the expected or the hypothesized successes But in a similar way to the confidence intervals and for the binomial, then we also need the same number of failures. And so we have to have at least 10 expected or hypothesized failures. Which means that n times q naught has to be greater than or equal to 10, right? And I'll just clarify where q naught is 1 minus p naught, right? The proportion of failures. Okay. So now we have those conditions, and what I'm gonna do is I'm gonna skip the second. I'm just gonna make sure that I have a random sample, and that's fine, or that I can assume a random sample, and then I'm gonna focus on checking these conditions instead. Okay, now, good. I think we're ready to tackle that example. Maybe what I should do, instead of having these on separate pages, how many lines do I have? 1, 2, 3? 1, 2, 3. Let's do 4. I realize that they're all off the page here. Well, they're all weird. Anyways, whatever. That's fine. Okay. So we have this example that I left you with last day. And so it's kind of a flip side of, or a very similar question to what we were working with before when we built our confidence intervals. And so I'm just going to copy this, whoops, and paste it here. So it's referring to the same survey, and we still have a sample size of 850 respondents, how comfortable they are with Facebook creating a list of categories for them. 41% of the respondents said that they are comfortable. Now, of the respondents tells me that this is my sample proportion, right? And so here I have p hat is 0.41, right? Because it says of the respondents. Now, do these data provide convincing evidence that the proportion of American Facebook users are comfortable with Facebook creating a list of interest categories for them is different than 50%? Wording's kind of weird, but, or long rather, but, right? So is there evidence, meaning that we have to do a hypothesis test? And so here, just as a side note, whenever you see evidence, that means you have to do a hypothesis test. Is there evidence that this happened? Okay. So that the proportion of American Facebook users are comfortable who are, maybe it says, maybe we should change it to who are comfortable with Facebook creating, is different from 50%. So now I have this sample proportion p hat, okay, and I want to compare that to 0.5, right? I want to compare it. How does it compare to 50%? And so this tells me that because I want to compare my sample proportion to 50%, this makes my p naught 0.5. Right. The value I want to compare my sample proportion to is 0.5. In fact, I want to know if it's different from 0.5. Okay. And so what that's going to do is, well, that means that I have a not equal to in my alternative hypothesis, right? And so we're going to step through this, this problem. And No better place to start than step one. Step one is to state the hypotheses. Oops. Oh, there we go. Okay. So we're going to state the hypotheses. If you did try this on your own, good job. And I know that finding this P naught is probably the most difficult part, right? And so that's going to take some practice, right? But whatever value you want to compare the sample proportion to, that's your P naught. Mm. So the null hypothesis here is going to be, whoops, P is equal to P naught, but now we replace that with 0.50. Okay. Generically, P is equal to P naught from your formula sheet, but we've already decided that P naught is 0.5, so now I'm hypothesizing that this population is centered on 0.5. Alternatively, HA, P is not equal to 0.5, right? And that's from, how can I? Here and here. Oops. There. Yeah. That's all you need to do in step one. I would argue it's the most difficult part because you're deciding what type of question you have. Once you've decided that, then you're kind of off to the races. But and then figuring out what P naught is, that's kind of tricky as well. I like to make a note here. Because I have a not equal to, this makes it a two-sided test. And you'll see why I make a note of that here. It's because in step 3, we're going to need to know, oh, do I have a one-sided or a two-sided test? And then I need to go back to step 1, which is really discombobulated, right? And so that's hard to keep track of. And so I like to make a note to myself that whether I have a one-sided or a two-sided test. Okay, so this is a two-sided test, right? And that's because of the not equal to. If I had a less than or greater than, I'm only concerned about one of the extremes, making it a one-sided test. I'm going to add a page here. So now we're going to check the conditions before we keep going. The independence condition. The first thing I'm going to say is I think the original question blurb said that it was representative. And so what we said for the confidence interval was we said we assume the sample was randomly sampled, right? So we assume the sample was randomly sampled. That's fine. The optional, I said I was going to skip it, but I am a slave to completeness. And so here we go. N equal to 850 is less than 10% of all American Facebook users. So the normality condition, this is the new one. The normality or the sample size condition is I need to have at least 10 expected successes. And so what I'm going to do is I'm going to calculate n times p naught. How many would I expect to have, right, in a sample of size 850 if the proportion was 0.5? Now, I'm not very quick on my feet, but I'm going to go 425, but I'm going to confirm. And for this, because no, be proper, Emily. What's proper? You should stack your equal signs, right? 425. 425 is more than 10. And so that checks out. So we have at least 10 expected successes. And n times q naught, well, that's 850 times 1 minus 0.5. 425 is still greater than 10, so it checks out. So therefore, the assumptions for the central limit theorem apply or are satisfied. Therefore, and I'm just going to summarize that as the assumptions. Well, maybe I'll write it out. For the CLT, the central limit theorem, are satisfied. Good. Now we can keep going. Step 2. Did I underline? No. There. So step 2, oops, is do the test. As we saw earlier from the formula sheet, we're going to calculate a z here. Z is p hat minus p naught divided by the square root of p naught q naught over n. Well, I have p hat is 0.41. I want to know how far is it from 0.5, which is my p naught. So z is 0.41 minus 0.50 divided by the square root of 0.5 times 0.5 divided by 850. Let's see if we can get something here. I'm going to focus on simplifying the standard error first. So I'm going to do 0.5 times 0.5 divided by 850 and then take the square root of that. Notice how I'm going quite fast, and that's because should have tried it already. So now you're just waiting to fill in the pieces that didn't work, right? And so I'm assuming that you've tried it already. 0.41 minus 0.50 divided by, I get 0.1, 714985851. So now if I do 0.41 minus 0.5 divided by that, I get a Z of negative 5.247856705. Yeah. All right. Now, in the next step, just trusting our gut, right? We know that, okay, 0.41 is less than 0.5, but is it significantly different from 0.5, right? It is different from 0.5, but is it significantly different? As a rule of thumb, any Z more than 2 in either direction is considered significant, right? Because that's a 95% confidence interval, leaving 5% in the tails. And so, so there's a direct link between the confidence interval and hypothesis test, but we'll leave that. But just as a rule of thumb, just to figure out if you're going to reject H0 or not, this is too far away, right? It's too extreme. So it's more than 2 standard errors away. And so we would say, unlikely. But let's keep going. Step 3, find the p-value. remembering that the p-value is the probability of seeing something as extreme or more extreme. Now, in this case, I wish. Uh, I'll show you this one because it's good to have seen it. Oops. Went away, I think. But I don't really like it because it's way out in the tails. So we had a z, let's put it here, z equal to negative 5.248, let's say. Okay. So this area here is the p-value, the probability of seeing something as extreme or more extreme. Okay. But we also have a two-sided test. And so for the two-sided test, we also replicate this as if it could have happened here. Z equals 5.248 here. Right? So we replicate it in the other tail. It only happened in one, but then we say, I would be equally concerned if it happened in the other tail. Right? And so now the p-value, right, is I'm going to show you two ways of doing it. Okay. So finding the p-value is let's see here, the area in the tail, which we know. So using the Z table, right, then we find that the probability that Z is less than or equal to negative 5.248 is approximately 0 or less than 0.0002. How do I know that? Well, let's go to the Z table. Well, I think I have it in here. Here. Okay. So we have a Z past negative 3.4. That's okay, or negative 3.49. And so that still exists. Oops. It's just less than 0.0002. Right. So here, right, the table goes to negative 3.49, and we're told that this area is 0.0002, right, just from here. Yeah. And so all we can say is that, well, then this area, which is way further out into the tail, is just less than 0.0002, which is approximately 0. You have to say approximately, right? Because it's not 0. At negative infinity, it's 0, right? Everything before then, it's approximately 0. Okay. And so it's very, very small. So even taking something very small and multiplying by 2, it's still going to be very, very small. Okay. And so the two-sided, or to find the two-sided p-value, we multiply the area in one tail by 2. So then the two-sided p-value, therefore the two-sided p-value is going to be, let's see here, move this over, is going to be 2 times the probability that Z is less than or equal to negative 5.248. There's a reason I used 3 decimal places that we'll see in a second, which is also 2 times approximately 0, which is approximately 0, or 2 times 0.0002, which is 0.0004. I'll say or less than. .0004, very, very small. Okay? Meaning that the probability of a sample proportion of 0.41, right, that's what we had here, coming from a population centered on 0.5 is very, very unlikely, right? And that gives us evidence to reject H naught. Now, what I don't like about this example is that it's off the table, so that's kind of hard to work with. And so what I want to do as just kind of an aside, not part of the problem, we'll continue with the problem, but consider instead, oops, p hat is equal to, now what would I have to do to get my z closer to something in the table? I'd have to move my 0.41 has to scooch closer to 0.5, right? It has to be within 2 standard errors. And so let me just do some maybe 0.46 minus 0.5 divided by, let me just make sure it works before I force you guys to do it. That'd be rude, right? Okay. 0.46, it works. Right? Then I would get a z equal to negative 2.33238078. So you can try that. But the reason I want to do that is just to show you how the p-value, how we would actually find the p-value, right? Because when we're saying approximately 0, that's kind of hard as a first example. I should have caught that. It's good to have seen it because it trips a lot of people up when you're off the charts, but it is possible. Okay, so now to find the p-value here, what we would do is consider instead if z is negative 2.3338. It's weird. What happened? Can you hear me?
I can hear you, but I cannot see you. There you go.
I hope you could see me earlier. Yeah, okay, good. Because I've been doing a lot of this, a lot of hand wavy motions. Okay, let me just make sure that it's all okay. Looks, that's never happened to me before, I don't know. So now if we had this z, which is on the table, so that's why I wanted to work with it, then what would this look like? Then the p-value, z is centered on 0, and if we have negative 2.33, let's say, from the table, we would find, okay, I need negative 2.33. So I'm going to copy that. Give myself another page. It's a lot of pages. Okay. And I'll put it there and I'll just zoom in. This tells me that the area in the tail, in one of the tails, is 0.0099. So I can jot that down and say, okay, this area is 0.0099. The one-sided p-value then is 0.0099. So using the Z table, we find the one-sided p-value is 0.0099. Oops. What I can do is I can say, okay, then the two-sided p-value is just 2 times that. Okay. Therefore, the two-sided p-value, which is what we want, is 2 times 0.0099. Don't forget a 0 there. 2 times 0.0099 puts me at 0.0198. Okay. So in our example, our p-value is approximately 0 or less than 0.0004. It's showing you a special case, and so that's why I wanted you to see this example. But what I also want to show you is we're going to use, so you can use the Z table to find kind of more exact p-values. At that point, you should probably be using Excel or some other software to find these p-values if you're interested in exact values. But what I want to show you today is how to use the t-table to find these probabilities. Okay. So now we can also use the t-table, which is the one that looks like this, where we're getting our confidence levels for the confidence intervals, right? And so then we said, well, down here at the bottom, I have a Z star line, which I'm going to use. And so now I'm just going to snag this part of the table. Hmm. We can also use the t-table to approximate probabilities or to approximate the p-values, to approximate the p-values or the p-value. Oops. And so that's kind of cool. And it is how I'm going to be proceeding uh, for the rest of the types of questions. And so, but I wanted to show you the link between the two. And then your assignment questions will say, use the t-table or use the z-table. And often I make you use both just to emphasize that you can use either. And so, same thing on the test, right? I could ask you to use the t-table or the z-table. And if you don't like the z-table, you can use Excel. Yeah? So let's see here. Notice we've got this Z star line. What's the first thing that we notice? The first thing that we notice is that all these Zs, right, these are Zs, are positive. Why? Because we have symmetry around 0, and so the area in the tails, we've already used this fact, the area in the tails is going to be the same regardless of which side of 0 you're on, right? If we're talking about the areas in the tail. And so then we can kind of save ourselves a little bit of paper and just use the positive side if we drop the negative. Now, I don't know how comfortable you are with mathy terms, but the first thing we notice the Z scores are all positive because by symmetry, right, the area in the tail will be the same on the negative side. Because by symmetry, the area in the tail will be the same on the negative side. So to do that, we're going to take the absolute value. The absolute value makes any value positive, so it just drops the negative essentially. And so to communicate that we are only using the positive value of z, we use the absolute value. Using the positive value of z, we use the absolute value. Might ring a bell. The absolute value of z is just the positive version of z. And so here, these vertical bars, right, and they're usually a little bit taller, this indicates the absolute value. And so here, how can I say it? There's a little bit of math behind it, but we don't need it. As long as you know that it turns any value positive, it turns z positive, right? So for example, the absolute value of z equal to negative 2.33, what was it? 2 is just 2.332. Yeah. The absolute value of z equal to negative 5.248 is just 5.248. Okay, so you just drop the negative. Okay, and that's because it behaves the same way. Now, let me see here. Or maybe I have that already. Okay, so what this line is telling us is this. If I have a z, let me just check the time here. Okay, good. So if I have a z distribution like this, trying to make it nice and lofty, z is centered on 0. Right, so here are my z's. They're centered on 0. This first value, I'll use orange. Something like this. 0.674. 0.674 standard errors away from the hypothesized population proportion is not very far, so we expect the area in the tail to be quite large. In fact, what this is telling us, notice that we have a one-sided P and a two-sided P. And so what it's saying is that, okay, if you need a one-sided p-value, then it's going to be 0.25. And maybe I'll do this. If you needed a two-sided p-value, right, then you have to replicate that in the other tail, which looks like this. Negative 0.674, which is also 0.25, together making 0.5. And what you'll notice here as well is that you really only need the one-sided p line, right? Because you can multiply by 2. It's done it for you, right? 0.2 times 2 is 0.4, 0.15 times 2 is 0.3, and so on and so forth. So you don't really need it, but it's nice to have it, right? And just as a reminder of which one are you looking for? Okay. What if your value fell between 0 and 0.674? Well, here at 0, what do we know about 0? 0 splits it in half. 0.5 and 0.5. Right? So that's a good check-in point. Let's go to Let's go to, I'll use purple. 1.96, right? From here, we can kind of figure out what the ones in the middle look like, but let's go to 1.96, give myself some space here. 1.960 from this table tells me that the area in the one tail is 0.025. Makes sense, right? If you have a 95% confidence interval, then your critical values are 1.96, and so the areas in the tail has to be 0.05, split evenly. Right, we get something that looks like this. Negative 1.96, 0.025. Looks a little wonky, but that's okay. Okay. And so here we have a Z line and it tells us the area in the tail. Eventually what you'll find is that, well, initially, let's start there. Initially, you might prefer the Z table. That's totally fine. We're used to working with the Z table. But eventually, I think you'll find that the T table is a little bit quicker, a little bit more efficient, and I think you'll gravitate towards using it. And so that's why I like to use it. And so finally, we have this point here. We know it's possible to have a Z larger than 3.291. Right? In fact, we could have 3.49 from our Z table, so we could go even further, but that's okay. We don't really need to, as long as we recognize that here at 3.291, the area in the tail is so small, 0.0005, multiplied by 2, it's still really small. Negative 3.291. 0.0005. What's the bound here? Well, the bound here, let's see. What color can I use? The bound here, let's pretend that it's at some point. Well, at some point, you'll reach infinity. And the area in the tail at infinity is 0. Right? So your bounds become quite weird once you've passed a Z of 3.291, but that's okay, because as long as you remember that the area in the tail at infinity is 0, then you're fine. Same thing down here. Negative infinity has an area in the tail of 0. All right. So what we're going to do is keep going with this problem here. Okay. Let's see here. So going back to our problem, right, we found for a Z of negative 5.248, right, is approximately 0 or less than 0.0002. Even when we multiplied it by 2, it didn't really make a difference. And so now, solving the problem, or maybe I should say finding the p-value using the T table. Oops. I'll highlight that because that's the difference from before. So if we want to use the T table, what we're going to do is we're going to say, and I'm always going to use the following structure. So although it's going to be a little bit weird in the beginning, you can always use this structure. Okay, and so where you're going to say or start is you can say since, and then what I do is in the middle of the page, I draw my absolute values. Okay, and so Z is equal to negative 5 point, I want to say 248. Let me check. Yeah. So the absolute value of negative 5.248 is just 5.248. And so is between two values. So what you're going to do to use this table is you're going to take your Z that you've calculated and you try to place it on this number line. Notice that they're increasing because you're moving out into the tail. And here, or if you prefer to have something like this, that's fine too, right? Because then you can see that, okay, 5.248 falls somewhere between 3.291 and infinity. So let's jot that down. 3.291 and infinity. That's fine. It's allowed. So I like to have these little link words. You don't have to, but this is where I remind myself. So again, I'm going to write in the center here because I'm going to have bounds on my p-value. And I'm going to remind myself if I have a one-sided or a two-sided p-value. My two-sided p-value and again is going to be between two values. Okay. In fact, if my, I'll start here. I'll do it here. Z is somewhere between 3.291 and infinity, then the area in the tail, even if I multiply it by 2, is going to be somewhere between 0 and the two-sided p-value that's associated with 3.291, so 0.001. Notice that you have to flip these, the order of these. It's going to be more obvious once we do. Hey, why did it do that? It gave me balloons. I don't know. I don't know. What is it? This? I don't know. Just keeps throwing balloons up. And so I don't know why, but I guess I need to stop using my hands or
Is
more hands.
It's your birthday today. That's why it's giving you balloons.
I know. Wouldn't that be so cool? It knows too much. No, mine's not till April, but I'll try it then. So here, our p-value, even if we multiply by 2, 0 times 2 is still 0. And the two-sided p-value associated with 3.291 is 0.001. So it's somewhere between 0 and 0.001. Notice that here we had to flip-flop a little bit, and the areas in the tails associated with these are flipped, right? Because our p-value, as our z's increase, the area in the tail gets smaller and smaller. And so I prefer, personally, I prefer to have the same inequality, right? From the lowest to the highest. Then I don't need to think about my inequality. Okay. In fact, I'm going to highlight all the things that are always going to be written down. So for the step, I would say since, and then this absolute value, or sorry, this less than, the absolute value of Z, and then the Z equals what it equals. Well, depends on the question, of course. And then whether it's a one-sided or a two-sided test, right? But in general, this is the, and I throw a so in there, why not? Right? Those things will always stay, right? Those will always be part of how we set up this solution, okay, and show our work. So now, consider the example just to show you what it looks like again, where Z is negative 2.332. And the reason, I guess I never mentioned it, the reason I keep 3 decimal places now is because the Z star line for this, for some reason, now has 3 decimal places, whereas the table only has 2. So you round your decimal places to match whatever table you're using, right? So now what we're going to do is we're going to say, let's see here. Is it in? Can I paste? Yes. So what we're going to do is we're going to take our, well, we're going to drop the negative, right? And then we take this calculated value, 2.332, and then we try to find where it would fall here, right? 2.332 would fall somewhere between 2.326 and 2.576. Now I know that I need a two-sided p-value, and so then I'm going to focus on these two, all right? So how I'm going to write this, following the same structure as I did up here, I'm going to say since, and I'm going to say the absolute value of Z equal to negative 2.332, notice that that's the calculated value, is between, right? And so I've got those inequalities set up. It's somewhere between 2.326 and 2.576. So the two-sided p-value right, is, and it's tempting to read it as in the same order, but you have to remember that, right, as we're moving further into the tail, the area gets smaller, so you have to read these in reverse, 0.01 to 0.02. Okay, so then our two-sided p-value is somewhere between, 0.01 and 0.02. What did we find using the Z table? Well, going back up here, using the Z table, we found that the two-sided p-value is actually 0.0198. Okay. So notice, using the Z table, we found the two-sided p-value was 0.0198. Well, is 0.0198 somewhere between 0.01 and 0.02? Yes, it is. Okay, that's great. Right, so it all checks out. So we have kind of a more precise way of getting the p-values, but what we'll find later is that we're okay with just getting these approximations, and then we use software to find the actual value. But notice that it does fall within this range, right? And so that's nice, right? And so it exists, it's somewhere in here, but we don't really, it doesn't really matter to us what it is exactly, right? Because from here, knowing that it's between 0.01 and 0.02, well, that's still very small in comparison to 0.05. So then we would reject H naught. Okay, so in terms of our conclusion, though, we have something even more extreme, right? For our actual example that we're working through, the p-value is somewhere, the two-sided p-value is somewhere between 0 and 0.001, right? We said it was less than 0.0004, right, which is in this range. Okay, fair enough. And if you wanted something more precise, you would have to use Excel or some other software. But I think we're ready for step 4, which is our conclusion. So the first time that we're seeing a conclusion with an actual p-value, or at least a range for our p-values. And so I'm going to write it out with the range because that's how we're going to be formulating these conclusions generally. And so I like to say, since our two-sided p-value, we have a two-sided p-value, since our two-sided p-value is between 0 and 0.001, right? Less than 0.0004 from the Z table. You don't have to do both, but for now, since I've been showing you both, I thought it might be nice. So you could say, since our two-sided p-value is less than 0.0004 from the Z table, or it's between 0 and 0.001, it is less than our alpha level or our assumed alpha level of 0.05. It is less than our assumed alpha level. I say assumed because the question didn't say using an alpha level of 0.01 or 0.1, and so I'm going to have to assume that it's 0.05, which is the default. So it is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught. Oops. To reject H naught. If I'm rejecting it, I can say in favor of what? In favor of HA. Now, what does that mean in terms of the question? That's the hard part. We're going to go, well, conveniently, I guess I have because I have the question here. So I'm going to snag that. And maybe what I'll do is just save myself some writing. Right? And I would say, therefore, these data provide convincing evidence that the proportion of American Facebook users, I guess maybe who are comfortable with Facebook creating a list of interest categories from them, is different than 50%. So you just reword the question as an answer. There is data, or these data do provide convincing evidence, or they don't if you fail to reject the null hypothesis. Okay, now let's see here. Okay. I'm a little bit, I think that's good. I know it's a couple of minutes early, probably, yeah, a little bit early, but I was running behind in my other section and I don't want to set myself up for failure next week and be all off kilter. So we're going to end it here. And if you have any questions, I'll stick around. But otherwise, I hope you have a great weekend and I'll see you on Tuesday. Stop this recording.